Yep, it's multiple choice, but you have to show your work on the test. Okay.
Is it always multiple choice?
Yeah, it's it's multiple choice. It's always questions, but you always have to show your work on the test. No work, no points. Okay. All right. So we are doing chapter 5. We'll do Newton's laws of motion today. Okay. So the first 4 chapters essentially were the subject of kinematics. Kinematics was about describing motion. Okay. And when we said, when we asked you to describe a motion, what we learned was we were asking you to give us this. Okay. The position of an object as a function of time. And once you had the position of an object as a function of time, okay, you could calculate its velocity, which was dr by dt. Okay. And then from the velocity, you could calculate acceleration, which was dv by dt, d square r by dt squared. Okay, so now we're going to start the subject of dynamics. Okay, so what you want to do is you want to change this motion. Okay. And what you learn is to change that, you have to apply a force. Okay. And that's what we're going to study. Okay. So the next couple of chapters will study that. What does it take to change a motion? Okay. All right, so Newton gave us these laws of motion, and this was almost 300 years ago, 350 years ago. Okay, and that's what we'll study. Okay, so these are the topics we'll cover. Okay, so Newton in almost 400 years ago. Okay, so he proposed scientific laws that we still use to describe the motion of macroscopic objects. Okay, what does that mean? I'm sorry?
Objects you can see.
Right. So Newton's laws do not apply for electrons moving around a nucleus. Okay? So for that you need newer laws, and those are quantum mechanical laws. Okay? So these Newton's laws apply to objects whose masses are, let's say, in the grams or kilograms and stuff like that. Okay. Newton also discovered the law of gravity, invented calculus, and made contributions in the theory of light. Okay? So he did many very profound things. Okay. Here's Newton's first law. Okay. This was actually discovered by Galileo. Okay. And now it's interesting because you don't see illustrations of this too often in real life. So for instance, you push an object and this thing, so I pushed this phone and it came to rest. Why did it come to rest? Friction. Okay, so in real life it's very hard to avoid friction. Okay, so but what again Galileo realized, what he did was, in the limit, as you keep reducing friction, that's when he realized the following law. Anyway, what we call it Newton's first law though now. Okay, the law states if there is zero force acting on the object, then velocity is constant. Okay. So if it is moving, it'll maintain its constant velocity, and if the object is at rest, then it'll remain at rest. That's when the net force acting on the object is zero. Okay. Now, the closest thing you see in real life is if you played air hockey. Okay. And what this layer of air does is it reduces friction tremendously. And you get the puck moving, and it'll move at a constant velocity till it hits one of the side rails. Okay. If you went into space and if you were far away from all objects, you throw a ball at 90 miles an hour, it'll keep going at 90 miles an hour forever until it interacts with something else. Okay. So that's Newton's first law. Okay. Now it turns out that this is a special case of the second law. The second law says when you apply a non-zero force on an object, then the acceleration is given by this equation. So the acceleration is proportional to the force and inversely proportional to the mass. Okay. And of course, now you can see that Newton's first law is a special case. If the force is zero, acceleration is zero, and velocity is constant. Okay. All right, so Newton's second law states what happens when you apply a force on an object. When you apply a force on an object, the object accelerates. Okay. All right, what are the units for the force? We'll almost exclusively deal with SI units. Mass is measured in kilograms, acceleration in meters per second square. So the units for force are kilograms, meters per second square. Yeah. And now in sciences, what we do is when you have a combination of basic set of units, we're sort of lazy. We don't want to write that all the time. So we give this combination of units a name, and we will give a new unit. And this is called a Newton in honor of Mr. Newton. Yep. All right, now here's another interesting thing about it. Okay, so let's look at this equation in a couple of ways. Okay. Again, you learned about equations. When you have apples on the left-hand side in an equation, what do you have to have? Apples on the right-hand side. This is a vector, and so this is a scalar times a vector, and that's a vector. Okay. So it's good that way. All right, how many equations? So here's another interesting thing about it. How many equations is that? I'm sorry? 3 equations. Okay, so it's actually in n dimensions, that's n equations. Okay, very good. So when 2 vectors are equal, their corresponding components are equal. Okay, so it's really 3 equations in 3 dimensions. So the x component of the left-hand side of the vector is equal to the x component. The y component is equal to the y component. Now here's another interesting thing it tells you. So what it tells you is if you apply a force in the x direction, you cannot change the motion in the y direction. All you can do is affect the motion in the x direction. Okay? A force applied in the y direction only affects the motion in the y direction. So that was the reason why we started off by studying one-dimensional motion, because you can, when you're making changes in one direction of the motion, the other directions are independent of that. Okay. All right. So again, Newton's second law states the way to give an object acceleration is by applying a force on it. Okay. Okay, Newton's third law says all forces come in pairs. So when she applies a force on the wall exerts an equal and opposite force on her. Okay. In fact, that's how you walk. So for instance, when you walk, what you're doing is you're pushing against the ground. Okay. And of course, you're relying on friction. If your leg slips, then you're not going anywhere. So when your leg doesn't slip, the ground applies an equal and opposite force on you, and that's what propels you forward. Okay. So again, Newton's third law states, for every action, there's an equal and opposite reaction. Okay. By the way, action and reaction are on two different objects. Okay. So here's an interesting consequence. Well, here's an interesting fact. So let's say you weigh 150 pounds. That means the earth is attracting you with a force of 150 pounds. So in turn, you're attracting earth with a force of 150 pounds. Okay. Mass is a measure of how much stuff there is in a body. Okay. Your weight is how strong the object you're standing on attracts you. Okay. So your mass is the same here on Earth and on the moon, but your weight on the moon is about 1/5 as much. Okay. Okay, so mass is just a measure of the amount of stuff in a body. The weight of a body is how strongly it is being attracted by the large body you're standing on. Okay. Mass is a scalar. The SI unit for mass are kilograms. Okay. Now, so there are multiple forces acting on her. Okay. So this girl is applying a force like that. That girl is applying a force like that. And what the superposition principle says is the following. Okay, so if on an object you apply two forces like this, F1 and F2, or this single force, where that net force is the sum of those forces, okay, if you look at the motion of this object, you can't tell if multiple forces acting on this object or a single force is acting on the object. Okay, so from the motion, you don't know how many forces are acting on the object. And that's the superposition principle. When several forces act on a body, the effect is the same as that of a single resultant force. Yeah. So going back to this equation, when the mass is 1 kg and the acceleration is 1 meters per second square, the force acting on an object is 1 Newton. Yeah. Okay, so gravitational force and weight, these are terms that we use in everyday life. So let's understand what this means. So let's say, so the earth attracts me with a force of 160 pounds. Okay. Force is a vector. It has magnitude and direction. The magnitude of the force is called the weight. Okay. So let's say if I went to Australia, there would be the gravitational force. Okay. So the gravitational force on me is a vector. This G is pointing towards the center of the earth. Okay. And your weight is just the magnitude of that force. All right, now we'll talk about a few forces that you encounter in everyday life and in problems. Okay. So this fellow is holding up this laptop. This is the force of gravity. That's the force that the earth exerts on the laptop. And the reason it's not falling down is because this fellow is exerting an equal and opposite force on that object. Okay. Now the way this force is exerted is the laptop is pressing down on his hands, the atoms compress, and it's an electromagnetic repulsive force. Okay. And that force is perpendicular to the interface of the two. That force is perpendicular to the surface, the interface. Okay. And that's why it's called the normal force. And you'll often see it written like so as well. Okay. All right. And you will learn that later this will become important. Friction forces will be proportional to this normal force. Okay. All right. So here's the force of gravity. Let's say I press down with an additional force there. What happens to the normal force? If the object doesn't move, the normal force increases. Okay? All right, so just remember that. So the normal force is balancing these downward forces. Okay, we'll look at objects moving on inclines. So if you have an object freely falling, that is the force of gravity is directly downwards, it falls down like that. Okay, that's the net force on the object. We'll be interested in objects that are sliding down inclines, and theta is the angle of the incline. Okay. And this object will accelerate down. Okay. And we would like to know the acceleration of that object. And it turns out that, okay, so the force of gravity is acting straight down like that. Okay, this angle is 90 minus theta. And if you draw perpendicular to the surface, now this angle will be theta. Okay. So this force of gravity, it's what's most useful in problems is the component of this force along perpendicular to the surface and along the incline. Okay. So what you want to do is, so this is the hypotenuse, complete this right angle triangle. So this is mg cosine theta. And this component is mg sine theta. Okay, so the force that is accelerating you down the incline is mg sine theta. Okay. All right, so that's what you want to remember. So for instance, and see, this thing makes sense. If theta were 0, sine 0 would be 0, and there would be no force accelerating you down the incline, because that would be a horizontal surface. If theta is 90 degrees, sine theta is 1, and you're just falling down vertically. Okay. All right, so again, let me clean up the diagram. And now this is all frictionless surface. Later on we'll add friction to it. Okay, so here's an object. There's the force of gravity acting on it. And all we have done on this slide is take the component of the gravitational force in two directions that are more useful. So this is mg sine theta, and this is mg cosine theta. Okay. So all we've done is broken this up into these two components. And they're the most useful components. Of course, you could break it up into any direction you want. You can do it like this and so on. I mean, you can do it, you can break it up into any components you want. Okay. This, of course, won't be as useful as this guy. Okay. All right. Now we'll talk about tension. Okay. A string is set, a taut string is said to be under tension. Okay. And when a string is under a tension of, let's say, 20 pounds, what does that mean? Okay, so what that means is the following. So when you have a taut spring, what you want to think of is a stretch rubber band. So when you have a stretch rubber band, whatever is attached to the rubber band, what is the rubber band trying to do? It's trying to become smaller. Okay, so this string is trying to become smaller. So what the string is trying to do is pull this guy in that direction and this guy in that direction. And so when we say the string is under a tension of 20 pounds, what this string does is it pulls this object with a force of 20 pounds in that direction and this guy with a force of 20 pounds in this direction. So that's what the tension in the string means. Okay, right now, in this course, we'll keep things simple. Okay. When the tension is the same, what the assumption that's gone in is this pulley is massless and frictionless. So all the problems we'll deal with, the tension will be the same. Okay. What do I mean by the pulley is massless? The mass of the pulley is negligible compared to these guys. Okay? That's what that means. Okay, as soon as the mass of the pulley is not negligible, friction is hard to take care of, so we'll always assume frictionless. But later on, you'll deal with problems where the mass of the pulley is not negligible. When the mass is not negligible, the tension on either side is different. Okay? So you will deal with those kinds of problems eventually. That's just an additional wrinkle in the problem, that's all. But right now, we'll deal with problems where the tension is the same. All right, so now that we've learned some stuff about forces, we'll just quickly talk about this. What is the idea of a bridge like this? Okay, so what is the difference between that bridge and this bridge?
On that bridge, the tension of the wires goes from above. That's where the arc is supported from above.
Right. So the reason we move from here is, okay, if you need 100 pounds to build this bridge, that other bridge can be built maybe with 25 pounds. You can build it a lot higher and so on. Okay. So for instance, if I remember my numbers right, the Empire State Building and the World Trade Center building, that's the difference was about 70 years, something like that. So for every 100 pounds used in the Empire State Building, there was 30 pounds used in the World Trade Center. Okay. And of course, the World Trade Center was stronger with less material. So what gives? The World Trade Center at the top would shake about 2 feet, apparently. I think so, if I remember the number right. Okay, so now the question is the following. If the building sways 2 feet, how come the windows don't pop out? Right?
The support sways with it.
What's that?
Like,
Well, I don't know the solution, but then here's another thing you have to worry about. Which is the most expensive floor on that building? The top floor. You got to make sure that the guy up there or the gal up there doesn't get dizzy. They paid all these millions of dollars. The Burj Khalifa at the top sways 2 meters. 2 meters is from here to there. All right. So again, the idea of these progress is, you're building bigger and stronger structures with less material. Okay. Now, one of the things this thing takes advantage of is the following. You will learn about this. So, for instance, so here's let's say this is a concrete pillar. I've just drawn it horizontally. Okay, and let's say you're trying to break this concrete structure by pulling on it. Okay, this is called, you're applying a tensile stress. Okay, and same concrete structure, this time you're applying a compressive stress. Okay. Which situation do you think will break the concrete structure first? I'm sorry? The top one? Yeah, so this will break first. You can apply a force almost 10 times greater. So for concrete, okay? So it's stronger under compressive stresses, okay? So this is the idea you're going to use in your building your structures. Okay, so let me show you what I mean by that. Okay, that's what's gone into this bridge. Okay, so what is it that you want? You want the largest forces to be compressive. Smaller forces can be tensile. Okay. All right. So I'm just going to make up numbers. So here's the bridge. And let's say the bridge with vehicles and all weighs 1 million pounds. Okay. So what do you want to do? So that's 1 million pounds. And okay. So what happens is, so the 1 million pounds is pulling it down. So what you want to do is, you want this to be 500,000 pounds. Okay, that's how it's being supported, 500,000 pounds. So you split the weight of this bridge. Okay, so this 1 million pound, 500,000 is being supported here, 500,000 is being supported here. You've broken it up into 2 pieces, and that's what's supporting it. See, this is a compressive force on these large structures, and these guys can bear the compressive forces. So how did you do that? Okay, well, here's what you did. You put in 1,000 of these cables. Each cable is lifting, the tension in each cable is what? 1,000 pounds. Okay, So the tensile stress on each cable is only 1,000 pounds. This guy is lifting it up 1,000 pounds, pulling down 1,000 pounds. All these forces get transferred here from all these guys. This is a large force. This is a large tension, and that gets transferred here. Okay. So that's the idea of these bridges. Again, bigger, higher, and less material. Okay. And also the idea is you want large forces to be compressive forces. Okay. What is the price you paid for this thing? Same problem as the tall buildings, lighter buildings, they sway. This thing sways much more compared to this guy. This guy is rock solid. Yeah. All right. Here are some of the forces that we measured and seen. Okay, so here's to stretch a DNA molecule, you need forces of the order of femtonewtons. Okay. Here, the weight of the Earth. Okay. A force of 10 to the minus 4 newtons on your eardrum, you can hear, and so on. That's the kind of stuff. The force on this wall of the dam is 10 to the 11 newtons. 10 to the 11 newtons, so roughly our weight is about 500 newtons. 10 to the 11 newtons is 500 million people. Okay? The weight of 500 million people. And of course, you don't want that wall collapsing. Okay? So again, here's in this dam, because this dam is built on has these strong rock walls, so the dam is built like that. Okay, so there's all the force pushing, that gets converted into a compressive force. So that gets pushed that way, and the wall pushes it back. So that's how this dam is strong. That gets converted to a compressive force. All right, what is this thing? What's this thing about? I'm sorry? I'm sorry?
Similar to an elevator?
Okay, so this is a pulley system, as its name suggests. And what this is useful for is, so this particular one, you can lift a 100-pound object with a 50-pound force. That's what it does. Okay, so it's a simple machine. Its mechanical advantage is the output force divided by the input force. Okay, so there's the output force. You're lifting a 100-pound object by applying a 50-pound force. The mechanical advantage is 2. Okay. What is the price you paid? Looks like free lunch to me. Yep. I'm sorry? Right. So every time you move this 2 feet, every time you lift it up 1 feet, you have to move 2 feet here. Okay, so we'll learn in a few chapters. Work out is always equal to input work. No free lunch ever. So force out times distance out equal to input force times input distance. This is assuming a frictionless surface. Okay. So this is a simple machine whose mechanical advantage is 2. here's a simple machine whose mechanical advantage is, well, this is also 2. 1, all you have to do is count vertical strings, okay, that go up. So that's 1, 2. This also has a mechanical advantage of 2. Okay, 2. This has a mechanical advantage of 3. 1, 2, 3. Okay, so you lift a 100-pound object by applying a force of 33 pounds. Okay. And again, since the tensions are the same in all the strings, what does that mean? That means the masses of these pulleys are negligible. Masses and frictions in these pulleys are negligible. This has a mechanical advantage of 4 if you're pulling it up this way. 1, 2, 3, 4. Yep. All right, so this has a mechanical advantage of 4. You can lift a 100-pound object with a 25-pound force. What is the problem with indefinitely increasing the mechanical advantage?
You're indefinitely increasing the distance.
Well, you're doing that. In practice, what would be the problem? Yep, very good. So more moving parts that are involved, you're increasing friction. Yep. All right, so you have to learn about springs. If you become an engineer, springs will be with you the rest of your lives. Okay, so let me show you. All right, so okay. Okay, so right now, what this is showing you is gravity is pulling it down, pulling this mass down, and so the spring force is pulling it in that direction. If I pull down on it, you see the spring force increased. If I pushed on it, the spring force decreased. Okay, so this is the equilibrium position. What happens in this system is if you disturb it, the forces that the spring applies will restore it to the equilibrium position. Okay, you disturb it in any direction, the forces that come into play are restoring forces. Okay. All right, so coming back to this now, we'll eliminate gravity. Okay, so here's the equilibrium position. If you compress the spring force is in that direction. It's restoring the system to its equilibrium position. If you pull on the string, if you stretch it, the spring force will try and bring the mass back to its equilibrium position. Okay, so what the spring is doing is, imagine a valley. You have a marble. The marble wants to be in the lowest potential energy state. You disturb it. The marble wants to come back. You disturb it. Okay, so this is a restoring force. On the other hand, if you put a marble on top of a hill, if you disturb the marble from the top of the hill, it doesn't come back. So this is not a restoring force. Okay. All right. Again, this spring example will be used everywhere. It turns out that for most springs, and if the deformation is not too large, if you deform it, okay, if you move the mass a distance x from the equilibrium position, the restoring force is proportional to the displacement. Okay, So when X is positive, the force is negative. K is the spring constant. Okay. It tells you how stiff the spring is. Stiffer the spring, bigger the K is. Okay. So, and when X is negative, negative times negative, the force is positive. Okay. So this is a restoring force. Okay. And you'll study this. So we'll use this all the time. Okay. And this law is called Hooke's law, after Mr. Hooke, who gave us this law. Okay. All right, this is just an interesting pulley system. Which way will this thing move? I'm sorry? It depends on the mass. Okay. So if M1 is greater than M2 plus M3, it'll move downward. Okay. And if M2 plus M3 is greater than M1, it'll accelerate upward. Okay. And of course, the final case is if it won't accelerate. If you get it moving, then it'll move at constant velocity. So here's an interesting application of this. Okay. So if M2 and M3 are greater than M1, it should accelerate upward. Okay. But what if we block the upward acceleration? And that's what's done here. So, okay, so in this diagram, okay, if you make the 4 buckets heavier than the table, okay, by the way, this device, there's nothing attached to it, no screws or anything. All you have to make sure is these buckets are heavier than the table, and the table wants to move upward, and then you're stopping the motion there. Okay. In fact, you could design it so that you can sit on this thing. You just have to make sure that the buckets have enough sand in them, and you'd be good. Okay. All right, here's one final fact we have to learn. Okay, so you learned the 3 laws, Newton's 3 laws of motion. The first law says if the net force is 0, acceleration is 0. F equal to ma is the second equation, second law, Newton's second law. The third law states action and reaction are equal and opposite. Okay, now those laws are valid in inertial frames of references. Inertial frames of references are frames of references that are not accelerating. Okay. So inertial frames not accelerating. So a non-inertial frame is anything that is accelerating. Okay. So for instance, if this room is at rest, this is an inertial frame. On the other hand, if you were on a merry-go-round and the merry-go-round is spinning, something going in circle is accelerating. That's a non-inertial frame. Okay. So in a merry-go-round, for instance, Newton's laws do not hold. Okay. All right, so let me give you an example of that. Let me illustrate that. Is the Earth an inertial frame? Why not? Well, it can move.
It's always
Spinning. There you go. Okay, so the Earth is spinning. But I mean, the spin happens. So if I throw this guy on, I threw this chalk piece and it went on a parabolic trajectory. this thing happened, this phenomenon happened over a span of 4 or 5 seconds or whatever, actually 2 seconds. And on that time scale, the Earth was at rest. But if you look at a phenomenon that happens over a time frame of, let's say, 2 hours, okay, over that time frame, the Earth spins considerably. Okay? And it spins each hour it's spinning 15 degrees, so 30 degrees it's spinning. Okay? So over that time scale, that's a non-inertial frame of reference. Okay? So here's an illustration. So imagine the following. Let's say Santa Claus is playing hockey and he hits a puck. Now, to observe the non-inertial behavior, you have to observe this puck over a span of 1 to 2 hours. Okay? Now, if you're observing this puck, let's say you're observing this puck, you're hovering in space, and you're at rest in the spacecraft, this puck to you it'll appear it's traveling straight. There was no force on it. Newton's first law says it maintains it's going straight, and it'll maintain its velocity, and Newton's first law works for you. Okay. If Santa Claus is observing this, what does he see? The Earth rotates, and what he sees is the puck is deflected like that. Okay? He hit it along the 0 longitude, but the puck has gone to negative longitudes. Okay? So Santa Claus is attached to a non-inertial frame, and he's seeing that there's no force acting on a puck, but it's being deflected. Okay? And so he believes in Newton's laws, and so what does he do? He says, oh, there must be a force acting on it. That's a fictitious force. He's got to come up with a fictitious force. A centrifugal force is like that. Okay? A centrifugal force is a fictitious force that you have to invent because you're observing things from a non-inertial frame of reference. Okay? Anyway, Newton's laws are valid only in inertial frames of references. Okay. All right.